Okay, welcome to the fifth video in the linear algebra and modeling sequence. This is called linear algebraic solutions. So we're going to consider again this system of linear equations that we've been working with. We've got this system here, y equals 3x minus 2 and y equals negative 5x plus 6. And what I'm going to do is rewrite this system of equations in matrix form. And this is probably something that you haven't seen before. And that's all right. We're gonna start from the beginning. So what I'm gonna do to start here is I'm going to rewrite these with both variables on the left here. So this is the first equation, and then this would be the second equation. Okay, so and then the next thing that I want to do is I actually want to change the variables, and this is fine. I can just rename variables as much as I want. It's just a name, you know. I can call it something else. So I'm going to call them both. I'm going to call x, the current x, I'm going to call it x1, and the current y, I'm going to call it x2, and that's going to be equal to negative 2. And so then we have 5x1 plus x2, and that's going to be equal to 6. Okay, so and I'm going to be using this dot product here to make these, right? So this is it's sort of weird to think about, but this is a dot product. So let's get that back there. All right, so this first equation is going to be the same thing as negative 3, 1 transpose times x1, x2. So I've made a vector of x1 and x2 and a vector of negative 3 and 1. And I've rewritten this equation as a dot product. So just have a look at that for a minute and make sure that it makes sense to you how that was done. And then let's do the same thing with the second equation. We're going to have 5, 1 transpose times x1. That looks like a comma. x1, comma, x2. All right, so I'm going to rewrite these. I'm actually going to rewrite these as row vectors and column vectors. So this is now going to become negative 3, 1 as a row vector times x1, that's a 3, x2 as a column vector, and 5, 1 as a row vector, and x1, x2 as a column vector. And then I'm going to rewrite, and that's equal to negative 2, and that is equal to 6. Okay, now here is the big leap. Here is where I'm going to change this into a matrix form for the whole system. So I'm going to turn each of these rows into a matrix. So this is going to become a full matrix here. And you know what? I'm using parentheses around my matrix. You might have seen matrices with brackets. It actually doesn't matter. I've seen them written different ways in different textbooks, and I actually like it this way. If you look at the Gilbert Strang textbook that I've sent you, you might see them with brackets, and it's equivalent. And then this is going to be multiplied times the vector x1, x2. And this works because this vector is being multiplied to each row. So this is being multiplied to this, and this is being multiplied to this. And then this is going to be equal to the vector negative 2, 6. And what I've done is I've changed each equation into sort of a row in my matrix computation. Now this is probably, you're looking at this and you're like, well, how does that help? That's really complicated. And it is complicated until you realize that I don't need to think about it in terms of the individual values. I can rewrite this in matrix form as A x equals B. And you see me putting a line above my vectors. That's because I can't write in boldface. So this is A the matrix times x the vector equals B the vector. And here x is this, it's x1, x2, and B is -2, 6. And this is what we want. This is what we're going to be working with. We're not going to be thinking about all of this. This is all really complicated. We don't want all that. We want this really simple, really clean matrix form for this equation. And this is what we're going to do with it. Let's scroll up here. So if we had some simple problem, right, like back to scalar arithmetic, say ax equals b, you can solve that pretty simply, right, by, you have ax equals b, and you can solve that by dividing both sides by a. And then you know that a divided by a is 1, so those cancel out, and you get x equals b over a. And that's how we solve this. That's an algebraic solution. Okay, but a better way to think about this is not in terms of division. Division is actually multiplication by the inverse. So the inverse of a, which we can write as a to the -1 power, is 1 over a. So if we have this equation, ax equals b, we can multiply both sides by the inverse. So 1 over a times ax equals b times 1 over a. Cancels, and I get the same thing. X equals b over a. And this is actually a better way to think about it. Think about it in terms of multiplication by the inverse. So when we're doing linear algebra, we should be thinking about, well, let's start with the identity, right? So when we have scalar values, the identity for a scalar value is the number 1. So if I have a scalar alpha, 1 times alpha is equal to alpha. The identity is something that doesn't change the original value. So we can multiply anything by 1 and we get back what we started with. So in linear algebra, with matrices, we actually have what's called the identity matrix. And so for a matrix, A, I, the identity matrix, times A is just equal to A. It's a matrix that doesn't change it, okay? So what's good about, when we think about the inverse of matrices, this is how the inverse is defined. So A inverse times A is equal to the identity. Okay, so if we have this, we got this earlier, right? We rewrote our system of equations so that we have ax equals b is the system. And if the inverse of a exists, we can solve this very simply in this fashion. So we have ax equals b. And we can multiply, here, I need a little bit of space here. We can multiply both sides by the inverse. Okay. Now A inverse times A is the identity, I. And I, the identity matrix times anything is, it's the identity. It doesn't change it. So we wind up with X equals A inverse B. And this is going to be the solution to our equation. This is going to give us the values of X that we are looking for. Now this is actually pretty straightforward in R. R has this function called solve. So we can solve a system of linear equations in R using this function. So we should talk about what this function solve does. So let's say we're going to solve 3, 6. Well, we get 2. So what we've solved here is the equation 3x equals 6. We're looking for a number so that that number is equal to 3 inverse 6, which is 2. So we're looking for, so if we had solve A comma B, that's going to be equal to A inverse B. We're going to get the result of this calculation. Solve A comma B is equal to A inverse B. Okay? So we could also do this for vector operations, right? So let's say we have solve, and I had to use this little transpose here. This was one of those cases where I had to use the transpose. It didn't work if I didn't use the transpose right here. A lot of times it won't matter. In this case, it mattered, so I had to use it. I needed to pass in a row vector in order for this to work. So I'm solving 2 times the vector 3, 6. So what I want is, this is going to give me the result of X equals 2 inverse times the vector 3, 6. And you can probably look at that and tell, oh, that's going to be 1.53. Right? 2 inverse is 1/2. So 1/2 times 3 is 1.5, and 1/2 times 6 is 3. Let's see if that's what we get from the, yep, we get 1/2, 3. So this solve function in R, if we have solve A, B, that's going to give us the result of A inverse B.